Okay, in this video I'm going to step through three examples. One is a repetition of the one that I did in the previous video, just for you to get another look at it real briefly. We have the integral of 2x times the quantity x squared plus 1 to the fourth power. And you note that we have function composition and that the inside function of the function composition has a derivative of 2x, and that 2x shows up on the outside and is multiplied by the function composition. When that happens, I can use the inside function as my u. I find the derivative of that, I solve that for du, and I go back to the original integral. You see that du is equal to 2x dx. So I can swap out the 2x dx and replace it with du. Then the inside function x squared plus 1 is equal to u. And so I can swap it out and replace it with u. Now when I put all the pieces together, I end up with just integral of u to the fourth du. And that is simply u to the fifth over 5 plus c, swapping out the u for x squared plus 1, and I'm left with 1/5 times the quantity x squared plus 1 to the fifth power plus c. And that's my final answer there. Okay, then let's look at another example. And that is the integral of 3x squared times the square root of x cubed plus 1 dx. Again, we're looking for function composition, and we have an inside function of x cubed plus 1. Its derivative would be 3x squared, which shows up on the outside and is multiplied times the function composition. And so we're safe to use x cubed plus 1 as u. We take the derivative of u with respect to x, we solve for du, and we're ready to go back to look at the original integral. If you notice that we have du is equal to 3x squared dx, and we have 3x squared dx. We're going to swap that out for u, and we have x cubed plus 1, which is u. Sorry, 3x squared dx was du, and x cubed plus 1 is u. And when I simplify now, I get simply the integral of the square root of u du, or the integral of u to the 1/2 du. When I integrate that, I get u to the 3/2 divided by 3/2, which is 2/3, times u to the 3/2 plus c. And I swap out the u for x cubed plus 1, and I get 2/3 x cubed plus 1 to the 3/2 power plus c, and that's my answer. Okay, I'm going to try one more, this time a trig example. And this time I have secant square of x times tan x plus 3. And this one and trig functions will be a little bit particular in this with this type of technique. They don't actually have to be, they could be, but they don't have to be a traditional function composition type problem or a typical function composition type of problem. But you're going to look for one of the factors here whose derivative is the other one. And so we know that the derivative of tangent is secant square, and the derivative of tangent x plus 3 is still going to be secant square of x. So tangent x plus 3 has a derivative of secant square of x, and that's going to help us identify tan x plus 3 as u. When I take the derivative of both sides, I'm going to get du dx is equal to secant square of x, and du is equal to secant square of x dx. And at this point, I'm ready to go back to the integral. And you notice that I have secant square of x dx, which I swap out for du, and I have tan x plus 3, which I swap out for u. Now when I rewrite, I simply get integral of u du, which would be 1/2 u squared plus c. And swapping out the u, I get 1/2 tangent x plus 3, quantity squared, plus c. And so these are the basic examples of using u substitution to evaluate integrals involving function composition and sometimes some more elaborate trig functions. I'll go on to some more examples of these in the next video.